Okay. All right, so we can relate our value of delta G to the equilibrium constant, and I mentioned Q and K, and this is why. So for our Gibbs free energy, delta G, and this is delta G with no not sign, delta G equals delta G naught plus R times T times the natural log of Q, where Q is equal to, just like what we saw in the equilibrium chapters. Okay. We can relate this to any value of our equilibrium, and we recall that at equilibrium, delta G equals 0. Free energy doesn't change. Also at equilibrium, Q is equal to K. All right. So this is delta G equals 0, and that's not delta G naught. All right, that's a different value. But if you say that delta G equals 0 and Q equals K, then I can rearrange this equation and write 0 equals delta G naught plus RT natural log of K, and rearrange that to do delta G naught equals R times T times the natural log of K. This value of K can be any of the K's that we've seen, KA, KSP, what else have we seen? KC, KB, all of those. It's an equilibrium constant. Is that a question? Yes, I forgot a negative sign. We usually put it on the right-hand side. Sorry, so delta G naught equals minus RT natural log of K. Thank you. What's that? Oh. Is it the Arrhenius equation? I don't know, actually. I'm not sure how this one was derived. But R is our gas constant, 8.314 joules per mole Kelvin. And T is our temperature in Kelvin. All right. Next time. Are there questions on this? Yes?
What's the difference between delta G naught and regular?
So we'll go into that more next time. The delta, don't leave yet because we have to do a pumpkin thing. This is the best part. Delta G naught is at standard conditions. We'll talk about it.
Don't worry about it.
Don't worry about it. So this is going to be loud. If you don't like loud noises, move towards the back or escape. Akash, yes. Well, I'm going to wear these because I'm standing right here. I was told that you can do this motion to your ears like this. That'll help, for sure. We're going to have to do that. Akash, since you have a helmet, would you like to be in charge of the fire extinguisher? In your bag? Yeah. Leave it on. I've got 2 fire extinguishers. Who's filming? All right, perfect. we are going to add to it, there's a container of water in here. We're going to add calcium carbide. When calcium carbide starts to dissolve in water, it produces acetylene. What's acetylene used for? Not quite bombs. It's a welding gas, so it's flammable. And so we are going to produce acetylene in this pumpkin, and then I'm going to light it. Okay? I've got all the gear. Those of you in front, definitely, or all of you, make cups, put them in your ears like that. All right. Not sure. No clue. If you don't feel comfortable sitting here, you really don't have to. I thought people should see this. All right, so I'm going to take 4 pieces of this. No, 5. It's bubbling. Woo. Okay. I'm supposed to wait 30 seconds, so we'll wait 40 seconds. I will. I got supposed to practice. There we go. I feel so disconnected from everyone with this. It's so weird. Has to make 30 seconds. Okay. Ready? Set. That's amazing. Yes. Uh-huh. Take a look at that here. So when we have something like delta G naught, so the naught stands for standard state. And there are certain properties that we expect for the standard state. Does anyone remember this from 1210? Yeah, standard state. Yeah. Yeah, so 1 atmosphere, 25 degrees Celsius. And if it's in a solution, the solution concentration is 1 molar. So if we're looking at a reaction and it's occurring at all of those standard conditions, if it's gases, it's taking place at 25 degrees Celsius and the pressures of the gases are 1 atmosphere, then we can say that's the standard state. If it's not at any of those, then we use the delta G or delta H or delta S without the naught symbol. And so that can be any condition. It doesn't have to be a concentration of 1 molar. If we're in solution, it could be 10 atmospheres, whatever it may be. The equation that was given in this slide allows us to relate what we know for standard conditions to what we want to figure out at non-standard conditions. Okay? So this equation allows us to make those comparisons. So basically saying how different from standard conditions is the delta G given whatever concentrations or pressures are existing. Okay? think Alexis, that was you that asked. Is that helpful? I think you asked that, right? Yeah. Okay. Does that make sense to everyone? So let's do it. We'll start off with a calculable problem, because we're gonna have a couple of these. I like this problem. This is a great example of calculating a delta G for an equilibrium. So let's calculating the equilibrium constant for the rusting of iron at 25 degrees Celsius. Delta G for this reaction, delta G of formation for the reactants, these are in their standard states. So these have a delta G in kilojoules per mole of 0. So iron in its standard state, oxygen, I said standard state, I apologize. What's the term? Not standard, it is elemental form, thank you. Yeah, elemental form. And then oxygen is diatomic in its elemental form. So then for iron oxide, the delta G is minus 743.5 kilojoules per mole. So from this, we're going to calculate delta G for the reaction. And then from there, we're going to calculate delta G, or we're going to calculate K, where delta G equals minus R times T times the natural log of K, the equilibrium constant. So in calculating delta G for the reaction, this is moles of products times its delta G of formation minus the reactants. And so we'll get 2 times minus 743.5 kilojoules per mole minus everything here is 0 on the reactant side. 4 times 0 plus 3 times 0. And so we'll end up with minus 1487 kilojoules, or in joules, minus 1.487 times 10 to the 6th joules. So from that value, we can calculate the equilibrium constant using delta G equals minus RT, natural log of K. We want to use joules because our R value is going to be 8.314 joules per mole Kelvin. So we're going to take our minus 1.487 times 10 to the 6 joules equals minus 8.314 joules per mole Kelvin times the temperature in Kelvin, 298, times the natural log of the equilibrium constant. So do that for me and see what you get. You've got a calculator. What do we get? Got an error. Anyone else get error? Great, you're doing it correctly. So this number is so huge that most calculators won't be able to calculate that. So we talked about rusting being spontaneous reaction. It's spontaneous and it favors products heavily, right? So because our equilibrium constant is huge, it's e to the 600. So I wanted you to see that value on your calculators because in case that comes up somewhere, somehow. But yeah, it's just a huge value. Okay, so if you got this far, great work. Questions on getting to the part where you can actually do any of the math? Anything on the equations, getting through those equations? You see why we did what we did? Is that part straightforward? Okay. Let's look at another problem then. So this one we're going to calculate a delta G, and this is going to be for non-standard conditions, okay? So here we have the formation of ammonia. We have N2 plus 3H2 forming 2NH3. Delta G naught for this reaction is minus 32.8 kilojoules per mole at 25 degrees Celsius. So for these partial pressures, which signifies we're at non-standard conditions, right? Because if we were at standard conditions, all the partial pressures would be 1 atmosphere. For non-standard conditions, with these partial pressures, what is delta G at 25 degrees Celsius? Okay. So the equation we're going to use here, delta G equals delta G naught plus R times T times the natural log of Q. Make sure you are using joules per mole for delta G naught. Okay. This is given in kilojoules. So we'll work through this together for the sake of time. Let's see, delta G naught is minus 3.28 times 10 to the 4th joules per mole, plus R, which is 8.314 joules per mole Kelvin, times our temperature in Kelvin, that's 298 K. Kelvins are going to cancel there. And then Q, or natural log of Q. Q is going to be equal to the partial pressure of the products divided by the reactants. And don't forget to raise to the stoichiometric coefficients, just like we calculated Q before in chapter 15. So our partial pressure of ammonia was 1.53. And that's going to be squared because of the stoichiometric coefficient of 2. We have 0.89. That's the partial pressure of nitrogen, raised to the stoichiometric coefficient of 1. And then for hydrogen, we have 1 times 10 to the minus 2, and that is cubed. Going through all of this algebra, we're going to end up with a delta G equal to 3.82 times 10 to the 3rd joules per mole. So is this reaction spontaneous? No, it's not. Delta G is positive, so the reaction is non-spontaneous. only those reactions with a negative delta G are spontaneous as written. If we reverse this reaction, we take ammonia, and it decomposes into nitrogen and hydrogen, that's a spontaneous reaction. Questions on that? All right. So just sort of a summary here. When we're looking at a relationship between delta G and the equilibrium constant, to use this equation, delta G naught equals minus RT natural log of K. If we have a reaction that's product favored, K is greater than 1, ln of K is positive, and delta G is negative, and so that suggests we have a spontaneous reaction. Okay? So we're working through like just looking at the sign for that mathematical equation. If reactants are favored, K is going to be less than 1. That makes the natural log of K a negative value, and when you multiply that by negative in front of the RT, you get a positive value of delta G, and that means you have a non-spontaneous reaction. So looking at the magnitude of K, whether it's greater than or less than 1, you can tell if a reaction is going to be spontaneous, okay, based on this equation. That make sense? Okay. Now let's take a look at how temperature plays a role in the spontaneity of reactions. Because up to this point, we've mostly been calculating delta G at 25 degrees Celsius, but we don't often or always want to do that or work at 25 degrees Celsius. We can make a reasonable approximation for delta G at any temperature by assuming that the enthalpy, delta H, and the entropy don't vary very much with temperature. Okay? This is not an approximation you're going to have to test. You're just going to assume that this is correct for this course, and it will be fine. Okay? And so, given this relationship, delta G at any temperature is equal to delta H minus T delta S. So this is something we have seen, but now we're going to try applying this to different temperatures. Okay? So when we look at calculating like a practical way of using this equation, you're going to have a, maybe you have to find a delta H value, and you have a table of values. Those table values are all going to be at 25 degrees Celsius. But that's totally fine, because we're going to assume that delta H and delta S are going to be the same, approximately the same, at 25 degrees Celsius at whatever temperature we're interested in. So for delta H and for delta S, these may both be at 25 degrees C. And we are going to figure out and use a desired temperature. So that's an okay way of doing that, right? So you're like, oh, well, my table for entropy isn't valid at 1,000 degrees Celsius. Doesn't matter, use that value anyways. So while delta H and delta S don't depend very strongly on temperature, delta G does vary greatly with temperature. And that's because of this equation. Okay. So I think we've got, yes. Okay, so how is spontaneity affected by temperature? So we have two options for the sign of delta H and two options for the sign of delta S. It can either be positive or negative. And when we combine those vectors together, we have a total of 4 possible situations. We can have a delta H that's negative, meaning exothermic, and we can have an entropy that's positive, so an increase in entropy. We can have an endothermic reaction, so a positive delta H and a negative entropy, and then the situation where both are negative, and the situation where both are positive. And so we can take a look at at the sign of delta G, and then and then be able to predict whether the reaction is spontaneous or not. So let's write our equation again, because we need to kind of see this equation in order to make some predictions here. Okay. So if we have a negative value for delta H, and we have a positive value for delta S, what's the sign going to be for delta G? Negative. Negative always, right? Okay. Which means that at any temperature, given a delta H of minus sign and a delta S with a positive value, at any temperature, the reaction will be spontaneous. Okay. If we flip the sign, and now we have a positive value of delta H and a negative value of delta S, what's the sign on delta G? It's positive, always positive, which means that reaction will be non-spontaneous at all temperatures. Okay. Now let's do a more challenging one. Not going to let me erase. All right, there we go. Let's say we have a negative value for delta H and a negative value for delta S. What's the sign on delta G? It depends on the temperature. So what happens if we have a high temperature? It's positive, very good. And so our reaction will be non-spontaneous at high temperature, and at low temperature, it'll be spontaneous. Does everyone see that? Yeah. Naomi.
How do you define like high temperature versus low temperature?
Great question. We'll come back to the positive. So how do we define high and low temperature? Great question. So we know that when delta G equals 0, what's true? What have we done before? Did I do this? Yeah. Let's go back to, let's think about this plot. Okay, let's go back to that plot, right? What's true when delta G is 0? We're at equilibrium. Okay? A reaction is at equilibrium. Is it spontaneous? No. If we have a reaction then that is no longer spontaneous because it's at equilibrium, we can say that if we set our delta G equals delta H minus T delta S equation equal to 0, that we can determine the temperature at which we switch from spontaneous to non-spontaneous. And so we can do so by rearranging and solving for the temperature. So if we subtract delta H from both sides and then divide by minus delta S, we'll get this. Minus delta H naught over minus delta S equals T. So we're just rearranging the equation to get that. What are the units on delta H? Usually kilojoules, we'll call them joules for now. What are the units on entropy? Joules per Kelvin. JK. And when you divide this out, look at the unit analysis. Our joules are going to cancel, and we're left with 1 over Kelvin. So we're left with Kelvin. So now we can calculate a temperature at which we go from a non-spontaneous reaction to a spontaneous reaction. On one side of this plot, we have a spontaneous reaction, and on the other, we have to push up the hill, and that's non-spontaneous. Okay, that's what this math is trying to tell us. Okay, so the temperature, the question about what's a high temperature and what's a low temperature, it depends on the reaction, it depends on the delta H, and it depends on delta S. So if you know delta H and delta S for a reaction, then you can predict you can calculate the temperature at which it switches from spontaneous to non-spontaneous. We'll do an example, but let's finish our table. So if we have a positive delta H and a positive delta S, we can have a positive delta G or a negative delta G depending on the temperature, and it's flipped in this case. So it's going to be non-spontaneous at low temperatures and it's going to be spontaneous at high temperatures. Okay. Before we do an example, are there questions on that? Questions on the table? Or getting to the filling out the table part? Okay. All right. So let's take a look at the reaction of calcium carbonate forming calcium oxide and carbon dioxide. And from our tabulated data, we have determined that delta H for this reaction is 198.3 kilojoules, and delta S is 159 joules per Kelvin. Look at our unit difference here. That's an important thing. That's an easy mistake to make when you do these calculations. Okay, so we want to determine the temperature at which this reaction becomes spontaneous. In the equation, or in the question, we know that it's not spontaneous at all temperatures. But if we go back to our table, because we have both positive values for delta H and delta S, we know that this reaction is going to be non-spontaneous at low temperatures and spontaneous at high temperatures. Okay. So in order to solve this, we simply we basically rearrange our delta G equals delta H minus T delta S and get temperature equals delta H over delta S. Make sure our units are the same. This time it looks like I've switched my the units of joules per Kelvin on the entropy to kilojoules. Doesn't matter which way you do this. We're going to have 178.3 kilojoules divided by 0.1590 kilojoules per Kelvin, and we end up with 1121 Kelvin. And don't forget, if you want to get this in terms of degrees Celsius, we have to subtract 273 to get our answer in Celsius. Okay. So below 848 degrees Celsius, this reaction is non-spontaneous. Above that temperature, it's spontaneous. That make sense? What time is it? Okay. So let's work on this one. I'll set this up and then y'all can work with your neighbor. So here we have a reaction at 40 degrees C. We have 2x plus y forms 3z. We're given a delta S for this reaction in joules per Kelvin and a delta G in kilojoules. Let's determine the value of delta H. Go ahead and work with your neighbor there. Just do this for maybe a couple minutes. Yeah.
There's a question on the homework that is the team having trouble? I think it was way off by it's just off by
Okay. I probably won't be able to like look at it. So if you want to send me like the problem number,
I have an answer.
I can send it to the publisher and they can fix it. That's at least I can do that. But it's very complicated. It's not the first time that. I can also.
Like we kept track of like 6.
Okay. How's this one? How's this problem? Is it okay? Yeah. Hopefully it comes down to a plug and chug type question. So we have a delta G equals delta H minus T delta S. We can rearrange our equation to solve for delta H. And really, the trick here is making sure your units are going to match up, right? So we're going to have our delta G of minus 45.6 kilojoules. We need our temperature in Kelvin. So that's 313 Kelvin. And then the delta S in kilojoules. So that's 0.0872. And I get minus 18.3 kilojoules. Everyone else, did anyone else get that? Great, I did it right. Totally. This one you don't have a slide for. Let's say you have a reaction of 2N2O4 dinitrogen tetraoxide forming 2NO2. What's delta H for this reaction? You don't have to give me a value. Is it positive or negative? Negative. Why do you say negative? Delta H. Let me draw one thing. Was that just a guess? Totally fine if so. What's their sign on delta H? Positive. Why is it positive? It's positive because we have to put energy into the system to break a bond. Anytime you're breaking a bond, the enthalpy is going to be positive. Okay? What's delta S, sign of delta S? Positive or negative? Entropy. Entropy increasing or decreasing? Decreasing, everyone reading, then increasing, then head shaking. Yeah, so we go from 1 molecule to 2 molecules. So whenever that happens, and they're both in the gas phase, everything's in the gas phase, we see an increase in entropy. So this is positive. Yeah, so we have more things, right? So that's just sort of the way I think about it. We have more things in the product side now. We have 2 gas molecules as opposed to 1. So they can be in more places, they have more microstates they can be in. Yeah, more moles. Is this reaction spontaneous? Yeah, depends on the temperature. At low temperatures, is it spontaneous? We have positive and positive. No, it's non-spontaneous. You might have to memorize this table or be able to reproduce it with your equation, however you want to do it. Probably better to be able to reproduce it. So at high temperatures, it's going to be spontaneous. Does that make sense? Don't ask me what delta H is going to be if we have more than a decomposition reaction. That's a lot harder to predict. Okay, questions on that? All right, let's do a slide here. Here we have a reaction of silver solid plus oxygen forming 2 silver oxide. We have a delta H and a delta S. Let's determine delta G for this reaction. That's the first thing. And then we're basically doing the same sort of thing. Determine the temperature at which the reaction becomes spontaneous. And then, yeah. Okay. You guys want to work on this by yourselves? Mixed results. How about I do this one, you do the next one? There's one more after this. Okay, so delta G at 25C is, we're going to use delta G equals delta H minus T delta S. Again, the units here are the big places to make mistakes. All right, so make sure your units are all going to cancel appropriately. we're gonna have minus 61.14 kilojoules for our delta H. Temperature, we're at 25C, so that's 298 K. And delta S, we need to convert to kilojoules per Kelvin. So it's minus 132 joules per Kelvin, so that's minus 0.132 kilojoules per Kelvin. Solving that mathematically, we're gonna end up with minus 21.8 kilojoules. Okay, so at 25 degrees Celsius, is this reaction spontaneous or not spontaneous? Spontaneous, yep. So let's figure out what temperature that this, oh, interesting. Yes, got it, okay. Let's determine the temperature at which the reaction becomes spontaneous. I'm glad I did this example because it just messed my brain up, which means it might mess yours up, so get ready, okay? So we're gonna use our T equals delta H over delta S. Watch our units, minus 61.14 over minus 0.132. And we're gonna end up with 463 Kelvin for the temperature at which the reaction becomes spontaneous. Or in Celsius, 198 degrees C. I told you it messed up my brain. I immediately went, oh, above that temperature it should be spontaneous, but that's incorrect, right? We have negative sign for delta H and delta S. So below that temperature, we're gonna have spontaneous reactions. So below 190 degrees C, we have a spontaneous reaction. Above that, we'll have a non-spontaneous reaction. So note that question B, the wording there, doesn't necessarily mean that it becomes spontaneous above a given temperature. Just temperature at which it becomes spontaneous. Make sense? Questions? Let's do more. Here we have a solubility of lead chloride. Lead chloride in equilibrium with lead ion and 2 chloride ions, and we have a delta G for this reaction. It's a positive value. Given all of these values for delta G of formation, so we have delta G of formation for the lead ion and for lead chloride solid, calculate delta G for the chloride ion. Let's do that. Go ahead and we'll take a minute or two on that, work on that together. Yes.
Set up any quality. With this not well, I got 146.
Yes. I believe that's what I got.
So when the temperature is less
I think that was your way better. What's now? Okay, so for this problem, we're solving for the delta G of formation for the chloride ion. And so we're using our delta G of formation for the product. Uh, Never mind. Let me erase that. Okay, so we plug in our value of delta G for the product. We have to add up then the delta G's for, oh my gosh, I'm so sorry, y'all. Okay, so we have our delta G for the reaction. That is given here. We plug in our delta G's for the products, multiplied by their stoichiometric coefficients, and then we're subtracting that of the reactant. We don't know one of the delta G's of formation for the product chloride. And so we're basically just going to do some algebra to solve for that, and I end up with minus 131.3 kilojoules per mole. Y'all get that? No? Did I do it wrong? You got that? Okay. Yeah. Watch your algebra on that one with the brackets and everything. Make sure you're adding and subtracting in the right spots because you have minus signs floating around everywhere. Okay. So then let's do the last thing here, calculate delta G at 25 degrees Celsius if our lead concentration is 0.024 molar and the chloride concentration is 0.077 molar. Which equation are we going to use? Oh, there's the question, yes.
Can you just write the equation for that?
Yeah.
Of it?
I'll try to write it correctly, but I won't use my memory because that seemed to have failed the last time. Where is it? There we go. Okay, so delta G of the reaction equals the sum of the moles of delta G of formation of the products minus the sum of the moles times delta G of formation for the reactants. I think that's on a slide somewhere. Probably looks a little bit neater there. Better format. What equation are we going to use for this last part? We're going to use the non-standard equation. Delta G equals delta G naught. Don't do it by memory, lady. Plus RT natural log of Q. Here we have our delta G naught. It's given in the problem, 27.11 kilojoules. R, we know R. We're going to be at 25 Celsius, and we have concentration, so we can figure out Q. All right, so we're going to have, looks like I converted everything to joules this time. I have no consistency there. Guess I don't want to convert R, that makes sense. So Q in this case is going to be the concentration of lead ion times the concentration of chloride ion, and we have to square that chloride ion concentration. And so that's going to end up being natural log of 0.024 times 0.077 squared. Doing all of that math, we're going to get 5.2 kilojoules. Questions on that? It'd be fun if we had something to explode today, maybe like a jackfruit or something. I don't. Maybe Friday. Yeah, you better show up just in case. This is the end of chapter 19. Alright, so we'll be starting chapter 20 next time. We need to remember how to do oxidation numbers and balancing redox reactions.